In this video, we're going to look at example 2 in section 8.6 of our workbook on power series. So ultimately, in this example, we are going to be computing an interval of convergence for a given series. That's going to be in part B, but let's get started with part A. So we're given this series here, n equals 1 to infinity of x minus 1 to the n over n. And this is a power series, we are told, for the function f of x, so for some function f of x, that appears in the diagram below. So we see here in this diagram that f is that dotted curve, so I can kind of fill that in here. Okay, and then what we're given in these images or diagrams are pictures of f along with various n-degree polynomials. So we see that we start with p sub 2, so that's this red line here, p sub 6, okay, p sub 10, p sub 14. Okay, so let's just sit and reflect on these graphs for a little bit. So notice that we can see right away, so where is this power series centered? We can see that that A is 1, and we see that, yes, indeed, that at 1, the function and the power series align. So now we want to consider, well, what interval around 1 does the polynomial look very close to our function? So we can see for p sub 2, it looks around here. P sub 6, we get wider. Maybe we agree on this interval. For P10, maybe we agree on this interval. And P14, maybe we agree all the way to, say, 0. But we see that regardless, we don't align outside or less than 0. So then it looks like, so part A, it says use the diagrams to guess the interval of convergence of the series. Well, as we get larger and larger n, even from 10 to 14 or 6 to 14, we see that it seems to be that the interval that we're going to converge on is from 0 to 2. So I'm going to say, looks like we converge on the interval where x is between 0 and 2. And so if we want to write it in the form of the interval that we saw in the previous example or that box, well, if x minus 1, so the distance between x and 1 is less than 1. Okay, that's the same notation for this interval. Okay, so now let's look at part B, where we're actually going to compute that interval of convergence for the series. And we'll see if we were right in our guess of part A. All right, so to determine that interval, we are going to use the ratio test. And this is the same procedure that you're going to use if you're looking at or considering the convergence of any series, power series you're given. Ratio test. Okay, so this is always how we start out. So what we need to do is consider the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Okay, so what is a sub n for us? Well, that's just the term in our series. So here is a sub n. So if we add 1 to n plus 1, we're going to get a sub n plus 1 is x minus 1 to the n plus 1 over n plus 1. Now I'm going to multiply by the reciprocal of an. So that would look like n over x minus 1 to the n. Oops, and I forgot my limit here. We should have a limit as n goes to infinity. I'm glad I dropped it though, because now we can kind of like sit with it a little bit and be like, oh yeah, maybe I forgot that in one of my homework problems. So I need to make sure I always include the n or the limit as n goes to infinity. Okay, cool. So let's continue working this out. So we can simplify some things. Notice I have an x minus 1 in the numerator and denominator. I have n plus 1 of them in the numerator, only n of them in the denominator, so we can cancel here. So we get the limit as n goes to infinity of x minus 1 times n all over n plus 1. So now we can separate this out a little bit. So notice this fraction is equivalent to the absolute value of x minus 1 times n over n plus 1. And now the reason why I separated it like this is so we can really see what that limit is playing with. So the limit is only playing with the n. So this x minus 1 has nothing to do with the limit. So I can pull that absolute value of x minus 1 outside of the limit. So I get the absolute value of x minus 1 times the limit as n goes to infinity of n over n plus 1. So let's consider this limit here as n goes to infinity of n over n plus 1. So notice here we have both the numerator and denominator going to infinity. That means we can use L'Hopital's rule. So that tells us this limit is equal to the absolute value of x minus 1 times the limit as n goes to infinity of derivative of n is 1 over derivative of n plus 1 is also 1. Limit as n goes to infinity of 1 over 1 is just 1. So this is equal to x minus 1 absolute value. So this is what we're getting for the limit in the end. So now let's recall the ratio test tells us that if this limit is less than 1, then our series converges. So this is that R that we get in the ratio test. So this means if x minus 1 is less than 1, therefore, series converges. So this tells us the interval of convergence looks like x minus 1 absolute value needs to be less than 1. And we actually saw that also with our guess. So one way that we see that absolute value of x minus 1 less than 1 is in fact this interval that we were first given here is by just identifying that center. So then we know the distance from x and that center has to be within whatever radius we were at. But there's another way we can unpack that. So stick with me here for a little bit. So notice what this statement is saying is that x minus 1 absolute value has to be less than 1. So that means that x minus 1 has to be less than 1 if our x minus 1 is positive. But also x minus 1 has to be bigger than negative 1 if our x minus 1 is negative. Because if, say, this x minus 1 was like negative 1.5, then the absolute value would be 1.5, which is bigger than 1. So we get this same interval going on here just from that absolute value interval. So then notice what we can do. We can add 1 everywhere. And this gives us then that 0 needs to be less than x needs to be less than 2, which is that first interval that we saw in part A also. Okay, so I'm just going to write some concluding statements here, but we're not done yet, and you'll see why. So we see that the series converges for x in this interval from 0 to 2 by the ratio test. But what about the endpoints? What about when x is equal to 0 or 2? So at x is equal to 0 and 2, what happens? The ratio test gives us that x minus 1 absolute value is equal to either, depending on the endpoint, 0 minus 1, which is 1, or absolute value of 2 minus 1, which is 1. And when the ratio test, that limit in the end is 1, the ratio test is inconclusive. The ratio test inconclusive on the endpoints. So this means we need to find another test to determine the convergence on the endpoints of our interval. So to approach this question about what happens at the endpoints, we're going to go ahead and plug in those values of x into our series, meaning plugging in x equals 0 and x equals 2, and then take a look at that series that we get and see if we can determine the behavior of the series. So let's look at when x equals 0 first. So if I just plug in x equals 0 into our series, what happens? So I'm going to go ahead and copy our series down just so we can see it on the same page. All right, so here it is here. So when x equals 0, that's way too thick. When x equals 0, we get the series of n equals 1 to infinity of 0 minus 1 to the n over n. So that just becomes the sum of n equals 1 to infinity of negative 1 to the n over n. So does this look familiar? Yeah, this looks like an alternating series. The terms go from positive, negative, where our bn is equal to 1 over n. So let's go ahead and evaluate the convergence of this series. So recall for the alternating series, we need the bn to be positive. We need the bn to go to 0. And we need the bn to be getting smaller. So bn plus 1 needs to be smaller than b sub n. So let's just go ahead and check these. So yep, we have all of these 1 over n is positive. The limit as n goes to infinity of 1 over n does in fact go to 0. And we do see that 1 over n plus 1 is less than 1 over n. In many ways we can check that. We see that n is less than n plus 1. So when we divide both sides by n and n plus 1, or maybe we'll do 2 steps. So divide by n, we get 1 is less than n plus 1 over n. If we divide by n plus 1, those n plus 1s cancel, and we see that we get that inequality that we want. Okay, cool. So what does this mean? So series converges at x equals 0 by the alternating series test. Okay, that's cool. Not bad. Got one endpoint down. So let's look at the other endpoint. So what about when x equals 2? Well, what does our series look like? Well, now we have the sum of n equals 1 to infinity of 2 minus 1 to the n over n. So what does that become? Well, 2 minus 1 is just 1. So we get n equals 1 to infinity of 1 to the n, which is just 1. 1 to the n always over n. So 1 to the n, 1 to any power is always 1. So that is just going to be 1 in that numerator. So I can just erase that numerator and write 1. All right, well, does this look familiar? Yeah, this is just a nice p-series. P-series, where our p is 1. That exponent on the n is 1. P-series with p equal to 1. So what do we know about p-series? Well, if p is 1 or smaller, we get divergence. So we can right away conclude that this diverges at x equals 2 by the p-series. All right, so what can we conclude then about the interval that we found of convergence in the earlier part? So in the first part of part B, we found convergence on the interval from 0 to 2, not including 0 or 2. In this last part, when we checked the endpoints, we found there was convergence only at x equals 0. So we can just summarize here. So in conclusion, we can write the interval of convergence looks like the following. So we're going to have 0 to 2. We're not going to include 2, so we're going to have that open or curved parenthesis. We are going to include 0, so we'll have a closed parenthesis. So that is equal to that interval of convergence. So notice I can also write this as 0 less than or equal to x is less than 2. So either way you want to write that is totally cool. Awesome. Great work working through this example.